Ladies and gents, today we're going to be talking about the dialysis technique. I'm going to be mainly discussing with you the most popular technique in dialysis, which is hemodialysis. My friends Yusuf and Bushra will be talking to you about the peritoneal dialysis and hemofiltration, which are the other primary types of dialysis. So to be able to talk about dialysis, I think it's good to give you an idea of how it was and what it became over time and how it is in the modern times. Let's discuss the history of it. In 1913, two scientists at Johns Hopkins Hospital were able to performed the first successful dialysis on dogs that were nephrectomized. That means that their kidneys were taken out. They were the ones who did it for the first time. In 1943, a Dutch doctor, Willem Johan Cruyff, was able to make a device that was the first working dialyzer, which he used very primitive materials such as sausage casings, beverage cans, and washing machine. And there's a picture here. As you can see, he made this device as a rotating wheel, which would help with the filtration process. We will later see, in the next slide, we will see that there's a different type that was also invented in 2 years after he did that. In 1945, Gordon Murray built another device, but this time it was not like a rotating wheel like Cruyff did. This was more like fixed plates. He was also able to develop this device independently. So we need to talk about why the dialysis procedure is needed. So basically, there are a number of things that can go wrong in our body, and kidneys are no exception to that. Sometimes people's kidney, they fail due to a number of reasons. And in these cases, to replace the function of these kidneys, we do dialysis. But there are different stages to the compromised kidney function, which in medical terms is called chronic renal failure. There are 5 stages, and these 5 stages are, they vary in the level of deformity, and stage 5 is the worst among them. And in fact, this is called the end-stage renal disease, and ESRD for short, and this is actually the stage that is treated with dialysis. And basically when you have kidney failure, you have to have your kidney function assessed, and depending on that, you're actually placed in one of these 5 stages. And in this assessment, glomerular filtration rate is used. So what is glomerular filtration rate? GFR. So basically, I don't know if you remember much about the high school biology that we've all taken, but in the kidneys, we have these glomerular capillaries, and these capillaries are surrounded by the Bowman's capsule. Now, what this capsule does is it takes out the waste products and the excess water from your capillaries, so that your capillaries would function properly, would not cause any problems in the other parts of the body. It takes out the urinary excretion. So, the glomerular filtration rate is basically the volume of the fluid filtered from the renal glomerular capillaries into the Bowman's capsule per unit time. Now, this measurement is actually, it requires sophisticated procedures. They need to be done by experienced personnel and specialized equipment. Because of that, because we don't have, so that we don't have to deal with these with these sophisticated procedures, we have this other thing called estimated GFR, estimated glomerular filtration rate. So in this determination of the eGFR, we use different equations, and one thing that they do look at is blood creatinine level. In addition to the creatinine level, we also have to evaluate the age, sex, and race of the patients, and basically these equations provides the basis for dialysis treatment and/or kidney transplant. You're placed in the respective stages according to the score you have. So now I'm going to be talking about I'm going to give you an outline of the different types of dialysis, and my friends will go into more detail on those. Well, when we did our research on dialysis, we saw that there are lots of different techniques. I think it was like 5. Obviously, we can't go into detail in all of these 5 types. But we also saw that they are categorized as primary and secondary, and we're going to be focusing on the primary devices, primary techniques. And so primary dialysis includes 3 different modalities: hemodialysis, peritoneal dialysis, and hemofiltration. Now you might ask me, what is the difference between the primary and secondary techniques? One thing to keep in mind is that these 3 primary techniques that I listed here, they are actually borrowed concepts in the secondary types of dialysis. For example, there is a dihemofiltration, which takes the advantage of hemodialysis and hemofiltration. So you can, if you were to be able to understand these 3 concepts here, you would also be able to understand the workings of the other secondary devices and techniques. So let's go. So we're going to start with the most popular type of dialysis. So there's the formal definition here: purifying the blood by providing means of extracorporeal removal of waste products such as creatinine and urea, in addition to excess water. So if you remember, these are also the creatinine and urea in addition to excess water. So these are also things that your kidney filters out. And I would also like to point to another word here: extracorporeal. What this means is it refers to the fact that your blood is filtered outside of the body. I don't know if you know much Latin, but corp, or in English, corpse means body, and extra means outside. So this means outside the body. So this is actually a term that was used multiple times in the literature. So I thought it would be appropriate to mention. So here we see a simple circuit here. And while we're going to be going into a much complex circuit in the coming slides, I thought it would be a good idea to put it here to talk a bit about the main parts. So as you can see, there is a pump, there is the arterial pressure monitor. These are important because we also want to make sure that while we're having the blood run through a device, we don't actually give the patient a hard time in terms of the blood pressure or other things. And we also have air trap. I'm sure you're all familiar with the problems that would arise if you have air bubbles in the circulatory system. And we also have the heparin pump. We're going to be talking about some of the problems that might arise in the dialysis procedures, one of which also includes the clotting, and heparin prevents that. So let's move on. So what is the working principle of hemodialysis? Hemodialysis is basically this. We have the blood in your body, we take that out, we pump it through the system, dialysis machine, and then we make it go through this filter. And while it goes through that filter, with the hydrostatic pressure that is produced, we are actually able to filter your blood. Now, in this device, we have this thing called pressure gradients. So what it does, it helps with the filtering procedure. We run fluids in this compartment of the dialysis machine in opposite directions. And these opposite directions actually produce the pressure gradient that is necessary. So here there's a very good picture. We have your blood taken out here. The blood goes into the dialyzer. At the same time, we have this thing called dialysate, which is basically a fluid that is used to filter out your blood. This is the liquid that receives the waste products from your blood, and we're going to be going into more detail about this fluid, what are its properties, but I just want you to focus on this section. The blood comes in here. The fresh dialysate that is prepared by your nurses, your healthcare workers, it goes through here, and the pressure gradient is created in here, and the waste products are filtered out here, and they're taken out into this container. And your clean blood follows this channel and goes back into your body. So here's a picture of the filter that is used. Filters that are used in the hemodialysis procedure. These are synthetic, and it's in the cylindrical container. It is vital to the working of the dialysis machine. So what can be the problems with hemodialysis? Since we're running the blood through an extracorporeal device, there is going to be a possibility of a low blood pressure. Pump might not work properly, maybe, or something else. There's a blockage. A number of things can cause this sort of problems. We can have muscle cramps. We can have itching, which is normal since we have the possibility of allergic reactions to some of the materials inside the semi-permeable membrane, which is the filter, synthetic porous filter. You can have sleep problems, and there's also fluid overload.
This section is about peritoneal dialysis. Let's start with the definition. Peritoneal dialysis is a technique that continues with a certain waiting time and emptying after the dialysis solution is infused into peritoneal cavity. Peritoneal dialysis is basis of the diffusion of solids between blood in the peritoneal capillaries and dialysate hypertonic solutions leading to ultrafiltration into the peritoneal cavity and the use of the peritoneum as a dialysis membrane. The peritoneal dialysis system basically consists of three principles: giving the dialysate to the peritoneal cavity, keeping it for a certain period of time, and emptying it at the end of this period. The giving dialysate into the peritoneal cavity and emptying are via catheters placed in the peritoneum. The catheters to be used for peritoneal dialysis must be bacteriologically safe, durable, and easily removable. The catheter is made of silicone, and there are many holes in the peritoneum to provide dialysate flow. Today, tank of catheters are the most commonly used for this purpose. And here you can see a Teknoff catheter. Left side of this point is inside the body, and right side of this point is outside the body and connected to a special set that is called Y set, and I will explain it later. And in this chart, we see that the peritoneal dialysate contains. What dialysate contains? Sodium, calcium, magnesium, dextrose, or glucose are used in the solution. Lactate is used as a base of the solution. But potassium is not used in the solution. Potassium is for hemodialysis solution. There are also different solutions such as icodextrin, solution containing amino acids, solution with neutral pH. And these different solutions were made according to patients and treatment. Okay. Types. Peritoneal dialysis consists of two fundamental types: continuous supplementary peritoneal dialysis and automated peritoneal dialysis, CAPD and APD. Automated peritoneal dialysis also contains three types: continuous cyclic peritoneal dialysis, nightly peritoneal dialysis, and tidal peritoneal dialysis. These three automated type, I don't tell them because automated peritoneal dialysis is enough to understand of concepts. Okay, working principles. There are two main logics in the dialysis: diffusion and ultrafiltration. You have also encountered this term in hemodialysis part, but let me talk briefly. Ultrafiltrations take place thanks to the osmotic differences between blood and dialysate created by osmotic substance. Water passes from the blood in the capillaries into the peritoneal cavity until osmotic equation between blood and dialysate is achieved. When the osmotic differences is highest, ultrafiltration is highest. Ultrafiltration decreases as the osmotic differences decreases, and ultrafiltration stops when osmotic equation is achieved. As a result of ultrafiltration, it is possible to recover more fluid than the dialysate given to the patient. Diffusion. When the dialysate waits in the peritoneal cavity, nitrogenous substances such as urea with high concentration in blood and other uremic toxins switch to dialysate by diffusion. Diffusion of solids is the fastest in the initial period when concentration differences is high. The diffusion rate decreases as the concentration differences between dialysate and blood decreases, and diffusion stops when the concentration of blood and dialysate is equal. After two terms, let's start working principles of CAPD. In this system, dialysate fluid is constantly present in the peritoneal cavity. The fluid in the peritoneal is discharged 3 or 4 times a day by the patient, and then a new dialysate is introduced into the peritoneal cavity. Until the next change, the dialysate remains in the peritoneal cavity. The most widely used system is the system where dialysis is exchanged with Y-set and twin bag. Okay, and what is Y-set and how does it work? I try to explain. Okay, there is a patient and catheters and other parts, we can say Y-set. In Y-set, there are two bags. This is dialysate bag and empty bag. And this bag also have clamps, dialysate bag clamps and empty bag clamps. Also, we can say this clamp is catheters clamps. Okay. Firstly, the clamp of the dialysis bag is closed and the empty bag clamp is opened. Dirty dialysis is transferred from peritoneal cavity to the empty bag with effect of gravity. Then the empty bag clamp is closed and the dialysis bag clamp is open. Clear dialysis is transferred to peritoneal cavity with effect of gravity. After transferring the new dialysis, the Y set is left from catheter and patient continues his or her normal life. And in CAPD system, there is no electrical device. We use dialysis, patient sets, and peritoneum as a membrane. Now I come back to previous slides. Okay, I told them in the definition parts the peritoneal dialysis consists of three principles: giving the dialysis to the peritoneal cavity, keeping it for a certain time, and emptying. Giving the dialysis to the peritoneal cavity is infusion. Keeping it for a certain time is dual, and emptying is drain. Infusion, dual, and drain is principles of peritoneal dialysis. At the left side, we can see the old system, CAPD system. We have a dialysis bag and empty bag, catheter, and we can say all about this Y set. And peritoneum is a membrane in our body, and abdominal cavity or peritoneal cavity, they are same. This is the CAPD system. Now let's look at the automated system. Okay. In this dialysis, the change takes place at night with the help of a device called cycler. Dialysis is given to the patient from cycler with a special set. Cycler automatically drains and refills the dialysis in the peritoneal cavity while the patient is asleep. In the morning, the connection with the cycler is interrupted. Here you can see a block diagram of automated peritoneal dialysis device. This block diagram is consists of temperature, pressure control, and flow rate control, pumps, motor and motor control, timing and control circuit, display, and microprocessor peak. I am going to try explain this part of the device, what they are and how this circuit works. And let's start with the temperature and pressure control. The dialysis, which is filled in the peritoneal cavity of the patient, is to be heated at a temperature of 37 to 40 degrees. This is to be controlled accurately as per the body temperature of the patient. Flow rate control. The rate at which the fluid is filled in the cavity should be uniform. This is also be controlled by a timing circuit. A timing circuit can also be used to control the flow of dialysate in the body. Pumps. Two pumps are required in the machine. One for pumping the dialysate from the bag into the cavity and another from pumping out the waste from the cavity after diffusion of waste. The function of pumps are controlled by peak and motors that have solenoid valves. Motors and motor control. Motor control the entire operation from flow control to pumping operation. Solenoid valves are open-closed circuit. When the dialysate is to be filled in the cavity, the motors open the valve and then the pump the dialysate from the solution back into the peritoneal cavity. After that, the valve is closed by the peak by sending a pulse. Timing circuitry. The timing circuit monitors all the operation since the machine is turned on until it shuts off. It also gives alarms when the machine is on, off, or any errors in detected during the process. Patient monitoring unit. Blood pressure and temperature of the patient is observed in this unit. If in some critical case, like the blood pressure of the patient increases, the peak and timing circuitry triggers the alarms. And the microprocessors peak. We use microprocessors in this device because of its features. These features is ideal for motor control, inbuilt 10-bit analog to digital convert, and low power consumption. These are the parts of the device. The last part is the peritoneal dialysis problems, but I won't tell them the problems because the video is getting too long.
What is hemofiltration? By definition, a technique in which water and solids are driven by a positive hydrostatic pressure across a semi-permeable membrane from the blood compartment from where it is drained. Hemofiltration is a technique mainly based on convection. What is convection? Convection is the process by which solids and solvents move according to the pressure gradient. During hemofiltration, an ultra-pure replacement fluid is reintroduced to the patient to maintain volume homeostasis. The effectiveness of convection mainly depends on the size of the dialyzer membrane pores. It has similar features with hemodialysis as hemofiltration: distribution volume and protein binding percentage. However, dialysate is not used with hemofiltration. Instead, a positive hydrostatic pressure activates the water. How does hemofiltration work? Hemofiltration works by removing large volumes of plasma water across the dialysis membrane using a pressure gradient or transmembrane pressure. The driving force is a pressure gradient rather than a concentration gradient. Hemofiltration requires a large flow of water across a semi-permeable membrane. This water flow is induced by the blood with pressure gradient to the filtrate side of the membrane. The water flux drags the solute through the membrane. The selectivity of the process is determined only by the sieving properties of the membrane. Removing large amounts of plasma water from the patient requires replacement. Substitution fluids, a buffered electrolyte solution similar to the plasma water composition, can be applied before or after the filter. There are also disadvantages of the hemofiltration. These are the complications arising from the catheter, clotting, bleeding, air in extracorporeal circuits, slow solid removal.
So now I'm going to be talking about the dialysate solution, which I mentioned that we would be going into more detail about in the previous slides. So there's again a formal definition, so let's go over that. A non-sterile aqueous electrolyte solution that is similar to the normal levels of electrolytes found in extracellular fluid with the exception of buffer bicarbonate and potassium. So there's also a note here. It is almost an isotonic solution, and 300 plus or minus 20 milliosmoles per liter. Plasma is 280 plus or minus 20 milliosmoles per liter. So with this dialysate solution, what we want to pay attention to is that we want to put in a solution that is similar to the blood in terms of density. What I mean by density is is it isotonic? If it's not isotonic, it's going to cause problems with your blood cells, such as red blood cells or other cells, because if you provide an environment that is hypertonic or hypotonic, you're gonna have problems with the cells. They might burst. So that is one thing to keep in mind. Another thing to keep in mind is that we also want to be able to filter out the things that we don't want in your body, the waste products. And this solution does that. This solution provides a density gradient sort of thing, and then it takes out the waste products from your blood and gives you back lets the rest of the blood go back through your body. And this fluid is actually used in only one single pass. So after that, it is flushed. And it also should be pharmaceutical grade, since it is the equivalence of intravenous solution. This is the solution that is commonly used in hospitals. And one thing also to keep in mind is how much product is used to filter out someone's blood. Each dialysis exposes the patient's blood to hundreds of liters of dialysate. That's how much is necessary to take out those waste products that we don't want. So here I put a table that I found in a book, and here it talks about what are the materials that are inside the dialysate. You see your sodium, potassium, calcium, magnesium, chloride, bicarbonate. We're going to be going into more detail about this part because this is an important component of the dialysate fluid. It actually balances the pH levels. We also have this non-electrode component of the electrolyte component of the dialysate solution, which is dextrose, which actually may or may not be used in your dialysate product depending on your doctor's preference. Your doctor can sometimes prescribe a dialysate solution to be prepared that doesn't include the dextrose. That is also another thing to keep in mind. These ranges are, yes, we have the ranges, but your doctor will be choosing something that he sees appropriate in terms of concentration, and your blood levels probably making comments due to your test results. So now we'll be going into detail about the electronic components of dialysis. So since we're engineers, I mean, at least we want to be engineers after we graduate, this is the part that that is important to us mostly. So here I put a more detailed circuitry of the fluid pathway, the dialysis machine. So we're going to be going into detail about these. I mean, at least for some of them. Some of them we're not going to go into that much detail. But we're going to be talking about the heating procedure, deaeration, proportioning pumps, conductivity probes, and also the valve systems, blood leak detector, all sorts of things. So, let's talk about what are the things that are monitored in a dialysis procedure. There are lots of things that need to be monitored because these things can potentially harm the patient if they're not monitored. There are always malfunctions with any type of device. There are always problems that are going to come up. So it is important that we have checks in place that would prevent these mistakes, these problems from harming the patients. So we have prescription here. This is basically, do we have the right components that doctor wants? The composition, this is basically determined by the conductivity and pH. We're going to be talking more about this. The temperature is an important aspect of this device, because one thing to keep in mind is that we have a certain body temperature, and our cells are accustomed to live in a certain range of temperatures. And inside the dialysis machine, the water and the dialysate, they're combined and they're heated, and this is done for various reasons. But it is important that it doesn't get out of control and get really hot or get really cold, which either can cause problems. We also need to check the flow. Is there flow? Is there blockage? We also check the pressure. We have to make sure that the blood pressure doesn't go out of its ordinary levels. If it does, it's going to cause harm to the patient. If there's effluent, there is absence of impurities. We have to check if the materials that we use to clean and disinfect are not there. These are obviously problematic for patients if it gets into their systems. Potential pyrogenic agents, these are the materials that can catch fire, and also microbiological testing. We have to make sure that there's no way that someone can get infections from this sort of dialysis procedure. So the first thing to start with is the first component of a dialysis machine, and this is the water inlet solenoid. Again, there's a formal definition. Let me go over that. Mechanical components that are used to shut off or control the fluid flow. Mechanical operation takes place when electromagnetic actuator. So this is basically done to control the flow in a precise way. Let's see how this component works. So here's a solenoid that is not necessarily used in the dialysis procedure, but it is a common tool that is a common component used in lots of different applications. But I thought it was a good image to talk about how it works. So basically we have this spring here, and we also have the wires surrounding it, and we're going to have electrical current coming here, and this electrical current will cause an electromagnetic field that will push the, in this case, pull the spring up so that this plunger will go up and it will enable the fluid flow. So as you can see, it's going to work. The spring is going to be affected by the electromagnetic current, and it will take the plunger up and the fluid flow will occur. So this is basically how it works. Now we have the temperature adjustment. So in dialysis procedure, the water is heated for several reasons. One of the reasons is that we have the cold water coming in that will be combined with the dialysate, but we have to degas it because we want to make sure that it doesn't really have any air in it, that much air in it. Also, we want to increase the mixing of the water and dialysate concentrate, and so that's one reason we heat it up. But again, it can cause problems if there's if the temperature level goes really high, and in this case, it would cause the red blood cells to hemolyze, which, as you remember from our biology courses, is bursting of the red blood cells. So it is very important to monitor the temperature, and that's why we usually, in the dialysis devices, a thermistor feedback circuit is generally used to control the temperature.
Thermistors are a kind of resistors and sensor. The most important feature is the change of resistance with the effect of heat. It is not a fixed value resistor but enters the variable value resistor group. Thermistors are made of semiconductor material. There are two types of thermistor: PTC thermistor and NTC thermistor. PTC thermistor consists of the initials of positive temperature coefficient expression. In other words, they are the elements whose resistance increases in the direct proportion to the temperature. In this type of thermistor, as the temperature of its location increases, the resistance value increases in that proportion. NTC thermistor is formed in the initial of negative temperature coefficient expression. In other words, they are elements whose resistance decreases inversely proportional to temperature. It is the reverse of the PTC thermistor. In this thermistor, as the temperature of this location increases, the resistance decreases in that proportion. This temperature sensing circuit uses a resistor in series with a negative temperature coefficient thermistor to form a voltage divider, which has the effect of producing an output voltage that's linear over temperature. The circuit uses an op-amp in a non-inverting configuration with inverting reference to offset and gain the signal, which helps to utilize the full ADC resolution and increase measurement accuracy. This temperature sensing circuit uses a resistor in series with a positive temperature coefficient thermistor to form a voltage divider, which has the effect of producing an output voltage that is linear over temperature. The circuit uses an op-amp in a non-inverting configuration with inverting reference to offset amplify to amplify the signal, which helps utilize the full ADC resolution and increase measurement accuracy.
Now we're going to be talking about a different component of the dialysis machines, which is the deaeration system. What the system does is it removes the dissolved gases by exposing water to the subatmospheric pressures generated by a vacuum pump after the heating of the water. This procedure is done for a number of reasons. Improper or inadequate removal of dissolved gases can cause many different problems. They can cause false blood leak alarms, false conductivity alarms, interference with volumetric control function, and decreased dialysis efficiency. So the last thing we want inside our fluid circuitry is air bubbles or any sort of dissolved air that is left inside the fluid circuit. So here we have a good image of this. We have the heated CO2, not CO2, sorry. We have the heated H2O water going in. There's the negative pressure, and the air when takes out the bubbles that are arising from the fluid flow, and the pump takes the fluid that is degassed. So another thing to talk about is the composition and the conductivity of the dialysate. As you remember from the earlier slides, there's a lot of things that are added into a dialysate fluid. This is totally depending on what your doctor prescribes you, but there are certain concentrations that are necessary to be adjusted in your dialysate, and after the preparation, 2 electrodes actually make sure that you have the right composition and conductivity in your dialysate. So the way that this is done is the 2 electrodes are placed in this dialysate, and they make sure that you have a certain level of conductivity to make sure that you have a good total ionic content in your dialysate that is proper for your body. So we found this picture again in a book. It is not really the best picture. I understand that, but there were no other better pictures. But I thought it would still be good to put it here because it shows you how. It basically shows you how it works. There are two electrodes again, and here again there's the there's a there's a there's a there's a piece that shows how much the conductivity is inside this fluid in Siemens, millisiemens. So we have this other component, which is the bypass system. This is the system that's gonna save you from getting hurt, getting harmed if there's something that's going wrong with the dialysis procedure. The other sensors that sense whether or not if there's high conductivity, high or low pH, or high or low temperature, once they actually signal that there's a problem, then the bypass system basically shuts down the fluid. It takes it out from the regular circuitry, and it stops the machine from delivering you the problematic fluid so that you wouldn't get hurt. As you can see, the bypass system takes the dialysate and diverts it to the drain. Well, we also have this other pressure monitor, which we will not go into detail, but we still thought that it would be appropriate for you to know that we also check the pressure in the filtration procedure. Dialysate pressure monitor monitors the ultrafiltration pressures. These are inside the filter that we talked about before. We also have this other thing which is called blood leak detector. So as you remember from the earlier slides, we have this synthetic porous membrane that's actually doing the filtering, and it would have blood on one side and the dialysate solution on the other side. Sometimes this membrane can be compromised, and when it's compromised, the blood might actually be going across into the, when I mean by blood is, well, blood components, some of the components of the blood, such as red blood cells. If it does that, we also have to make sure that the procedure is stopped because blood should never cross the blood dialysate barrier, and we detect the leakage via the blood leak detector, and this is located downstream from the dialyzer, from the filter. As you can see, there is a good image here. We have the dialysate in, dialysate out. Sometimes we have red blood cells here, and the light source sends photons, and if the photocell detects there's an anomaly, there are things that are not supposed to be there, then the system is stopped. These are our references. Anyone who would like to get more info can follow up with these. Thank you for listening to our presentation. I understand that this is a bit longer than expected, but we wanted to make sure that everyone has a very good understanding of the dialysis procedures, both the physiological processes and also the engineering aspects of this technique. So thank you very much.